you see on the board, we have the results from test 2. Average was a little lower this time at 69.74, but still rounds to a 70. High grade was greater than 120. Low grade was less than 30. In order to calculate your grade that I reported on Blackboard, you need to take your number correct, divide that by 23. Multiply that ratio times 100%, then add in any bonus points that you earned. If you didn't try the bonus, then you have NB instead of bonus points listed there. Right? That should equal the number that is in Blackboard. If I made a mistake with the calculation, as always, just let me know politely. We'll get it fixed, no problem. All right? Now, as far as the questions that were discounted, the top row, all of those were discounted. They were all missed by 49%, 54%, 55%, 49% of y'all. So I just threw those 4 out. Then, for the next row, I split the difference. 48%, 48%, 47%, and 48%, so close to half, but not quite half. So I gave you 2, I kept 2. So 6 total questions discounted. So your highest grade could have been out of 23, although somebody I think actually made a perfect score. So anyway, if you have any questions about the grades, etc., please let me know. If you want to see your personal performance on the test, it's advising, so I'll have my advising schedule up. Just go ahead and go to the chemistry department website, make an appointment with me, and we'll be 15 minutes, 30 minutes, whatever you would like. Ready? All right. So does anybody have any questions about anything before we go ahead and dive in? Yes.
I have a question. For the last question for the extra credit section, where it said you can put whatever you want.
Yeah.
Were we supposed to put multiple things to earn
Sure.
more
You can put as much
points?
as you wanted to.
Could we have earned more points though, or just
I think it ended up being worth 4 points total. So yes, if you gave me if you listed 4 things that you studied that were not there. Now, a lot of people, just so that y'all know, and you'll see this if you come to see your test results, a lot of people listed things that actually there were test questions about. So I gave you a point for effort, but that was it. You just got 1 point there.
Okay.
But yeah, you could have conceivably earned more. And in general, I don't know, I'm an effortist. That means I discriminate on the basis of effort. The harder you try, the more I'm going to try to help you to do well. So always on these bonus questions, put down as much information as you possibly can. Try your best to get the right answer. I will give as much partial credit as I feel comfortable doing. So, but yeah, you could have gotten more points than one if you put more than one thing. That was not on the test. There were a few people that were confused about what wasn't on the test. Yes. All right. Any other questions about anything? Okay. Well, when we left off last time, we had introduced the concept of Avogadro's number. So we want to go back to that to get started today, as we do over here. Now in your textbook, you'll find that Avogadro's number is represented by a capital N sub A. We represent it with a lowercase n when we talk about moles in general. So when we talk about the Avogadro number, it's a capital N, it's a number, it's a counting number. The sub A stands for Avogadro, and this number does not need to be memorized, but you'll probably use it so much that you will get it memorized. And it tells us that 1 mole of anything, we can talk about people, we can talk about sand grains, we can talk about camel spit molecules. 1 mole of anything is equal to 6.022 1415 times 10 to the 23rd of that thing. So Avogadro arrived at this number somewhere in the neighborhood of about 1850. What a lot of people don't know is that back in about 1780, Benjamin Franklin, one of our founding fathers, actually estimated the number as well. He turned out to be wrong only by a factor of 4. He went with 1.5 times 10 to the 23rd instead of 6 times 10 to the 23rd. But considering that both of those numbers are in the same range, the same power of 10, 10 to the 23rd, that's actually pretty doggone impressive. So a lot of us know about the kite flying experiment where he got electrocuted, but very few people do know that Benjamin Franklin actually came up with a number for the mole and he was only off by a factor of 4. And that's really pretty impressive, considering he did it 70 years earlier than Avogadro. And it was a really neat experiment. What he did was he took a tablespoon of oil and he let it spread over the top of the lake. And then he made the assumption that the oil layer was exactly 1 molecule thick all the way across. He calculated the area that it spread out into, and then he estimated the size of what he thought an atom would be, and he came up with his number. So we don't really have to worry about that too much, other than it's historically interesting. But we do need to know that Avogadro does give us a number, and we need to be able to work with it. Now, where this number becomes especially important is if we work with really tiny objects. And so atoms and molecules, those are perfect. Right? And so at the very end of the last class period, what we did was we recognized that this number at the bottom of the box on the periodic table is what we call the atomic mass. If we're talking about 1 carbon atom. And so we actually have the units that physicists have suggested. We call those AMUs. However, if we scale up, and instead of just talking about an individual molecule, and rather talk about 1 mole of those molecules, here we're talking more about carbon atoms. If we talk about 1 mole of carbon atoms, it turns out that 1 mole of carbon atoms, 6.0221415 times 10 to the 23rd carbon atoms, weighs the exact same number, 0.011 grams. And so from this relationship, we now come up with what is called the molar mass. So this is the mass in grams for 1 mole of that object. And the molar mass is 12.011 grams for 1 mole. And so the numbers don't change. All we've done now is shifted from talking about single individual atoms to talking about moles of those atoms, or single individual molecules, talking about moles of those molecules. So we just need to make sure that we understand the numbers themselves are the same. The units we use change for the situation. All right. So now that we recognize molar mass, which will abbreviate M period, we want to recognize that the molar mass itself actually falls into 3 distinct categories. There is what we call the atomic weight. Now, why did they suddenly shift from going to molar mass to atomic weight? When they talked about atomic mass earlier, well, I think that's part of the problem. They already tied up atomic mass for 1 atom. So now, if we're talking about a mole of objects, we talk about the atomic weight, which would be abbreviated AW, and specifically, that would be for elements. And so we have our example, carbon. And so the atomic weight, the molar mass of carbon atoms, 12.01 grams per mole. Where we do need to make a distinction is whether we're talking about ionic compounds or covalent compounds. Remember, covalent compounds exist in nature as individual discrete molecules. But ionic compounds, they're just a giant lattice. And so although we can identify a formula unit, which is the empirical formula for that particular chemical substance, there's no true molecule that exists with an ionic compound. So when we talk about the weight here, because we have the formula units, are empirical. We can talk about this for ionic compounds. And also acids. So you'll see FW reported for ionic compounds. You may remember when you did the salt experiment. At that time, we really hadn't talked about this too much, but we did know that they were all ionic compounds. And on the bottles, they listed FW, formula weight. So, classic example here. We're using sodium chloride all along. Sodium chloride has a formula weight of 58.44 grams per mole. And we calculated that number at the end of last class period. Okay. And then finally, when we have covalent compounds, the smallest discrete unit that we work with is called the molecule. And so we have molecular weight, which is abbreviated capital M period W period. And for water, that value is 18.02 grams per mole. And so I just want you all to get used to the jargon and also recognize there's a reason behind everything that we do, all this strange vocabulary that it seems like chemists work with. We're just trying to be as specific as possible so that there's no confusion or ambiguity. All right, so let's go ahead and practice calculating a molar mass for a chemical compound, mercury 1-phosphate. Now, I know right off the bat that I'm going to be calculating a formula here because this is an ionic compound. We're going to go ahead and construct the ionic compound. Does anybody remember how we represent the mercury 1 cation? Okay, here. It's Hg sub 2 because it's diatomic with a 2+ charge. Because each mercury atom or each mercury ion carries a +1. So the 2 added together, that gives us +2. Phosphate was the idea on the bonus question, but a lot of y'all kind of shied away from that. So I don't know if it's because you didn't know what phosphate was. What is the chemical formula for phosphate?
PO4.
PO4, very good. I like that. Nice and automatic. And what is the charge on phosphate? -3. Or your book will write 3-. Now this won't become important really until chapter 4, but students sometimes ask, how come sometimes you put the plus or the negative sign in front, and sometimes you put the number in front? Well, your authors conform to this concept, which I don't really think you need to worry about too much right now. I don't care if you write +3 or -3, -3- or 3+. However, usually to indicate that we are working with an ion, they put the number first followed by the charge. And so we're treating these as ionic species. So we'll write the number first and then the charge. And then when we do the crisscross method, we end up needing 3 of the mercury 1 cations and 2 of the phosphate anion. Right? And so in order to calculate the formula weight, we need to recognize that we have 3 times 2. We have 6 mercury atoms. And from the inside front cover of your book, mercury comes in at 200.6. Okay. Then we have 2 phosphoruses. So 2 times 30.97. And then finally, we have 2 times 4. We have 8 oxygens. So let's get a number for each one of these. So these are the numbers my calculator gives me. Hopefully everybody else's calculator is giving the same numbers. Some chicken. So we're confirmed. Now, we need to go ahead and take into consideration that number 200.6 has 4 significant figures. So when we're about to do this arithmetic, this addition, we have a value that is accurate only to the ones place. 30.97, 61.94, both of those have 4 sig figs. And then 16.00, my calculator doesn't give me 128.0, but I need to go ahead and do that because that fourth zero is significant. Right? And so when I add these numbers together, 1203.6 plus 61.94 plus 128. My calculator gives me 1393.54 grams per mole. So first things first, everybody else in that same number. Okay, very good. Now, to what place should I record this answer?
4.
To the ones. Very good. Number 1203 only extends accurately to the ones place. Therefore, any following calculations would have to either have 4 sig figs or, for addition and subtraction, be reported to the ones place. And so, when I do that arithmetic, I recognize 4 sig figs is because there were 4 sig figs in 226. And to the ones place is because 1203 only extends to the ones place. And so the formula weight, which is also the molar mass, the formula weight is more descriptive, is equal to, well, you tell me.
1394.
Very good. 1394. We need to round up that last digit. And so 13.94 grams per mole. Right? And so all the skills that we've been working on are starting to culminate. We need to be able to do all of them. We can't let the earlier skills go. We have to be able to continue to work with the skills we've learned previously. All right. Oh, and I wanted to draw a picture of this. So we have 5 ions that are basically going to be bumping up against one another. So remember, we have to have alternating positive and negative. So we would start with an Hg2, 2 plus, and then there would be a PO4, 3 minus, and then there would be another Hg2, 2 plus, and then another PO4, 3 minus, and then finally, and so that is how we could represent that. So that if we threw it in the water and it decided to dissolve, all of those ionic bonds would break. But the bonds that hold these polyatomic ions together do not. All right. So, now that we have molar mass, it turns out that we need to be able to do calculations with it. And so, just like the relationship we had for density, that some people see more easily using the little triangle. We have the same type of a relationship here. And so from these triangles, we have every relationship that we need. Mass is equal to the density times volume, or density is the mass divided by the volume. Molar mass, we already got that, molar mass is grams per mole. So grams is equal to molar mass times the mole of the substance that we have. Or the number of moles is equal to the grams divided by the molar mass. Now, your textbook also relates this relationship that is more akin to doing dimensional analysis. So in your textbooks on page 96, they show the relationships between mass and amount, and then finally, number of entities. And to go back and forth between mass and moles, so that mass is in grams, amount is in moles. We just need the conversion factor that relates those two units to each other. And so the molar mass allows us to interconvert between grams and moles. If we want to interconvert between amount and moles and the number of particles, well, this is where Avogadro's number is very helpful. Okay. So, I don't mind which method works best for you. Find it, use it. I'm going to demonstrate dimensional analysis though. All right. And so let's take a very specific amount of a very specific substance. Let's start with 45.71 grams of zinc. So we have all these zinc atoms. We can weigh them on the balance in lab. 45.71 grams. We want to convert these to the moles of zinc. And then finally, we want to know exactly how many zinc atoms that actually turns out to be. Okay. So, standard dimensional analysis procedure here. Every arrow in our path corresponds to a vertical line in the dimensional analysis grid work. We start with the information given. That goes in the upper left-hand corner. In the very next panel, we put the unit that is in the numerator of the first panel in the denominator of the second. Then, we know that at the end of this step, we want our answer to be moles of zinc. And so voila, we have the molar mass that we can use as our conversion factor here. And from the inside front cover of the book, is 65.38 grams of zinc for every 1 mole of zinc. So this is just the molar mass, exactly as they show us in figure 3.2. Then, in order to go from the moles of zinc to the number of zinc atoms, we need Avogadro's number. And so we remember that for 1 mole of anything, it's 6.0221415 times 10 to the 23rd. So that's our conversion. Right. And I'm writing all of these units out in full detail so that you can see exactly how they work. Numerator of 1 cancels out with the denominator in the next. Then the numerator of the next cancels out with the denominator of the next. And we have the units that we need at the end of our calculation. All right. So I'm going to do the first step here. I'm going to stop for a second. So let's get that number, 45.71 divided by 65.38. My calculator gives me 0.699143, 469. Right. So is everybody else's calculator giving them the same number? I see some head shaking, yes. Now, if I stopped here, if I had to report this answer on a test, how many sig figs should I report this answer to?
4.
Very good. There are 4 significant figures in our starting information. Therefore, I need 4 sig figs if I were to stop at that point. But I want to continue, so I still have that number in my calculator, the full number. Now, I want to go ahead and multiply that times Avogadro's number. So, let's do that. When I do, my calculator gives me 4.2103, 408.99 times 10 to the 23rd zinc atoms. So again, first let's make sure everybody gets the same numbers. Okay, good, I see some head shaking, yes. And how many sig figs for this answer?
4.
Also 4. Now this is where we need to stop. So I'll go ahead and write this answer out to 4 significant figures. 4.210. That 0 has to be included, God bless you, because it's a terminal 0. And terminal zeros always go at the end of the number if their decimal point is significant. So 4.210 times 10 to the 23rd zinc atoms. So if you have a 45.71 gram sample of zinc, we expect it to have 4.2103 times 10 to the 23rd zinc atoms. Everybody okay with that? Next, everybody see that number? Everybody else is here. All right, so that's our first use. Now let's do the same thing for water. So, let's start off with 73.73 grams of water. And then from that, I want to calculate the moles of water. I also want to calculate the number of water molecules. And then we're going to branch off. I want to calculate the actual number of hydrogen atoms. And the actual number of oxygen atoms that are also in that system. Right. So, dimensional analysis grid work. Let's just go with the top line right now. So there are 2 arrows. Therefore, we need 2 vertical lines. 73.73 grams of H2O. In the second panel, we put the molar mass. 18.02 grams per mole goes in the denominator. 1 mole of water goes in the numerator. And then Avogadro's number. So again, we'll do the arithmetic piecemeal. First, we'll convert to 73.73 grams to moles. So I've written the number up on the board, 4.09 and some change. Everybody else working along getting that same number? Okay, good. I see at least one head shaking, yes. All right. Now, we multiply that times Avogadro's number. And my calculator gives me the number I'm writing on the board now. So again, please check your calculator. And if you're getting the same number as I am, okay, good. I see at least one head. 2. All right, so that's good. We're pretty much confirmed. All right, now, how many sig figs should we report each of these answers to if we were stopping at that point? 4. So, we have 4.092 moles. And we also have 2.464 times 10 to the 24th. Water molecule. Right. And so is everybody in agreement with this? All right. So now what we want to do is we want to go from the molecules of water to the number of hydrogen atoms to the number of oxygen atoms. Let's do oxygen first. In the stoichiometry of our water chemical formula, for every one water molecule, there is one oxygen atom. So I can turn that into a conversion factor. Right. When I do that, I end up with the exact same number of oxygen atoms. Right. So, even if I had kept all the digits that I had written, the 2.463998, etc., it would still round off to 2.464 times 10 to the 24th oxygen atoms. Now for hydrogen, I'm going to have to multiply this number times 2. So I'm going to use the full number again. 2.46399, 295 times 10 to the 24th. Water molecules. And now the relationship is, for every one water molecule, there are 2 hydrogen atoms. So I have to multiply this number times 2. So is everybody okay how we can use the strength of the dimensional analysis grid work to go ahead and calculate something that doesn't really seem to be a conversion, and yet it is? Because a conversion is any time we find a relationship between 2 quantities and then carry out the calculation. Right? So these are the number of oxygen atoms. These are the number of hydrogen atoms that are present in a sample of 73.73 grams of water. We'd even take this a step further if we wanted to. If we add these 2 numbers together, we can calculate the total number of atoms that are in 73.73 grams of water. And when I add these together on my calculator, I get 7.392 times 10 to the 24th. And now we're not discriminating, we're just saying atoms in general. Some of them are hydrogen, some of them are oxygen, all of them are part of the water molecule. is everybody okay with, and or can everybody see, how we can now extend the use of dimensional analysis into areas that are just beyond a simple 1 mile is equal to 1.6 kilometers kind of thing?
How can you use the sig fig, the 4 sig figs for the 1 oxygen atom, and then do the double number for?
Okay, because as I explained, I know that the ratio between oxygen atoms and water molecules is exactly the same. If I had used this full number, I would have gotten 2.463999, et cetera. So just to save time, I went ahead and wrote it this way. But because here I had to multiply the number times 2, I needed to make sure that it would really truly double. And so that's why I went ahead and used the full number there. Technically, you could have used the full number here, but you would have rounded exactly the same. So we just saved one step by doing it this way. Okay?
For the hydrogen atoms, you would run that down for sig figs as well?
Right here, once we get the answer, we should round that up. And I'm so sorry, I should have done that. Thank you. So 4.928 times 10 to the 24th. I'm sorry. Yes, I should have gone ahead and reduced it there as well. Everybody else okay with everything else? All right. Well, there's in my mind, shorter way to do this. Some students see it. For others, it's not quite as clear cut. You don't have to do it this way. But if you can see it, it helps you to stop having to write so much in the dimensional analysis. So if we have H2O with our 2-to-1 hydrogen to oxygen ratio, we know there's also 1 oxygen for each water molecule. So if we have 2.464 times 10 to the 24th water molecules, then I can just use by the 1-to-1 ratio the fact that there is also 2.464 times 10 to the 24th oxygen atoms. I don't have to write everything else down over there on the right-hand board. I just recognize stoichiometry is a molar ratio. I have the stoichiometry from my chemical formula that's written correctly. And for every 1 mole molecule, or for every 1 water molecule, I have twice as many hydrogen atoms. So 7.392, I'm sorry, 4.928. And so this is an example of how all we are working with here are proportionalities. We're working with ratios. If we had 6 water molecules, how many hydrogen atoms would there be? 12. And how many oxygen atoms would there be? 6. Now the point to be made here, if we work with numbers that are more reasonable to us, we can see this immediately. But the point that I want to make sure that you're understanding is, even if the numbers look weird, they're still the same ratio. This is still a 2-to-1 ratio, just like 12 to 6 is a 2-to-1 ratio. So, if you can see this, and it helps you, do it. If it doesn't, this is always fail-safe. Dimensional analysis is always going to be our fallback, because dimensional analysis will never fail us. Right? All right. So now let's go back and talk about single replacement reactions, how to recognize them, and a couple of questions that I got after y'all did the lab last week. Please remember, the way that we can identify a single replacement reaction is we start off with 1 element and 1 chemical compound. And so if I have solid calcium and I drop it into liquid water, I've met the requirements for a single replacement reaction. I have an atom, an element, and a chemical compound. Now, we need to remember, for right now, we're replacing B with A. And so on the product side, we get new element B plus new chemical compound AC. But when we work with water, and we've seen this illustrated at least once previously, we have to recognize that we have to think of water just as any other chemical compound, with a positive portion and a negative portion. And so instead of writing H2O, it's better if we write H-OH, where we have a positive 1 proton combined with a negative 1 hydroxide ion. As soon as we do that, we can also see how it's easy for the calcium to replace the hydrogen, which means that on the product side, hydrogen gas should bubble out of the system. Now, you also confirmed this in lab because you ran the pop test. And so a positive pop test tells us that hydrogen gas was definitely created. The other thing that we did for this system in lab was we tested it with litmus paper. And when litmus paper turns blue, well, the B in blue reminds us of the B in base. And so we know there also had to be a base formed in this chemical reaction. The base itself would have to be a hydroxide with a metal. Well, the only metal in the system is calcium. And so remembering calcium is an alkaline earth, it gets a +2 charge. Hydroxide ion has a -1, +2, -1 crisscross, gives us CaOH2. Now, soluble or insoluble in water, which is the same thing as saying strong electrolyte or weak electrolyte. 50-50 chance.
Insoluble.
Okay, insoluble. Have one vote for insoluble. Anybody want to play devil's advocate? All right, then I will. Let's put a vote up for soluble.
Insoluble.
Another vote for insoluble. Okay, well, let's take a quick class vote. How many people think it might be insoluble? Okay, how many people think it might be soluble? Oh, you also learned to trust me much more. How many people aren't thinking? At least you're honest, that's very good. Now, there was a list of 8 strong bases that was listed before you all went home for spring break. Didn't necessarily expect you to know them for the last test, so I didn't ask any questions about it. But certainly, over spring break, I would have hoped that you would have spent the time to memorize something that I basically told you was crucial to your future development in chemistry. Well, there are 8 strong bases. Strong bases are strong electrolytes. Strong electrolytes are electrolytes where every single formula unit associates. If every single formula unit associates, then we call that a soluble compound. So the calcium hydroxide here, quite soluble. It's one of only 8 strong bases. If you don't have those memorized, do it. Because you never know when I might give you a pop quiz and say, here, I'll add these points to your last test grade. So, calcium hydroxide, well, actually, let's just do it real quick. All of the column 1A metals, lithium hydroxide and cesium hydroxide. We ignore francium because francium is present only in trace amounts in the earth. But from lithium hydroxide down to cesium hydroxide, all 5 of those are strong bases. And then we shift over to the alkaline earths, calcium, strontium, and barium hydroxide, also strong bases. We'll explain why in chemistry 112. For right now, though, you memorize the information. In 112, it's explaining. So please make sure that you all get those 8 strong bases, as well as the 6 strong acids. You gotta have those memorized too. All right, so we now have what's essentially our molecular equation. And in order to balance it, I only have to do one thing. Does anybody see that? Just that one thing I have to do to balance this equation.
Put a 2 in front of H2O.
Very good. If we put a 2 in front of the water molecule, then we have 2 H's that turn into hydrogen gas, and we have the 2 hydroxides that are needed to make calcium hydroxide. All right. The other reason it's crucial that we know that calcium hydroxide is soluble is because in order to write the total ionic equation, I have to be able to figure out what is aqueous in solution so that I can write it as its component ion. So I start off with solid calcium, and then water. Well, that doesn't dissociate. Right? And then on the product side, I have hydrogen gas that bubbles out. And I have my soluble calcium hydroxide. And so the only substance here that's aqueous is going to be calcium hydroxide. But if this were a single question on the test and you didn't know the calcium hydroxide was soluble, you get the whole question wrong. So we need to make sure that we understand why or what the solubility rules are and how they work. This gives us our total ionic equation. And then for our net ionic equation, what we're going to do is we're going to eliminate any chemical species that occur on both sides of the reaction arrow in the same form. Well, calcium is solid on the left, and it's calcium 2 plus on the right, so that changes. Water is liquid H2O on the left, and on the right-hand side, it's broken down into hydrogen and hydroxide. So, hydrogen gas, and then the calcium and the hydroxide are different on the product side than they were for the reactant side. So that changed. So in our total net ionic equation, they have to be included as the ions that they are.
How come you get from the 2 now and from the H2O?
And so, voila. We haven't seen this previously, but both the total ionic and the net ionic equations are exactly the same. Now, you will see this a lot as you start working with these single reactions. Right? Step by step, don't take shortcuts. Make sure you're practicing everything we're trying to teach you. Yes?
The 2 plus charge on calcium, it comes from the OH group.
What comes from the OH group?
The 2 plus charge comes from the
You mean the fact that there's a 2 here?
No, could you put it there?
Okay, I'm sorry, we're looking at our conversation. Just let me ask 1 second, sorry.
So could you put it on the calcium on the product
Calcium
side?
2 plus?
Yeah, but not on the reactant side?
Right, because over here it's elemental.
Okay.
It doesn't get the, okay, this is an important point, and we'll get to this at the end of chapter 4. If we have any element and it's in its elemental state, we don't give it a charge. We only give it a charge if it combines with another chemical substance. So, hydrogen here, H, technically has no charge. But in water, it has a +2 and oxygen has a +1. Negative has a negative, oxygen has a -2. So we need the 2 plus here because that's what we have. We have a calcium 2 plus cation, as opposed to elemental calcium that is not combined with anything else. Is everybody kind of okay with that? We'll talk more about this at the end of this chapter. All right. Any other questions about any of this? Okay. So, the title of chapter 3 is the Stoichiometry of chemical compounds and the Stoichiometry of chemical equations. Now that we've done a number of different equations balanced, it's time for us to remember, and we stated this before as well, the Stoichiometry of a balanced, so it has to be balanced for this to be true, of a balanced chemical equation is the set of the empirical molar coefficients. And so once we balance a chemical equation, we have the stoichiometry for that equation. so just as the subscripts in a chemical formula tell us what the stoichiometry, the ratio is for that chemical compound, these molar coefficients tell us what the stoichiometry is for the balanced chemical equation. So that's why we go to all this trouble of making sure that we satisfy the law of mass conservation by balancing the chemical reactions that we run. Now, we've used this example quite a bit as well. Does anybody remember the type of chemical reaction this is?
Double reaction?
No, it's
No,
not a double.
it's not.
It does start with a D though.
Displacement?
Not decomposition. Decomposition when something falls
Direct
apart.
combination?
This is direct combination reaction. The only significance there is we might as well practice it every chance we get. So this is a direct combination reaction. What we really want to focus on right now, though, is a set of empirical molar coefficients. Right. And so I have a 2:1 ratio of the hydrogen to the oxygen to the water. Now, suppose I had 5 moles of O2 that could react. How many moles of hydrogen could react? 10. Very good. Remember, we want to maintain that 2:1 ratio, so 2:1, 10 to 5. How many moles of water could we make?
10.
Also 10. Right. Now, these relationships are the bread and butter of what we're going to be doing for the rest of chapter 4. So let me rephrase this statement a little better. Yeah, there's a 2:1 ratio of hydrogen to oxygen, so if I have 5 moles of oxygen, I'm going to need 10 moles of hydrogen. But let's go ahead and state that. So how many moles of H2 are required to react completely with 5 moles of O2? Because that's really what we've just answered. That's technically the question that we've answered. If I have 5 moles of oxygen and I want to react it, how much hydrogen do I need to react all of that oxygen completely? Right? And so this value that we just calculated is referred to as a stoichiometric amount. Based on the stoichiometry of our balanced chemical equation, how much hydrogen do I need to react with this much oxygen? We call that the stoichiometric amount. And so on a test, they unfortunately won't phrase it. How many moles of H2 are required to react completely with 5 moles of O2? They will say something along the lines of, what is the stoichiometric amount of hydrogen required for 5 moles of O2? So I want to make sure that you all are getting used to the chart. Everybody okay with that? Now, on the product side, this 10 moles of water is also a stoichiometric amount. Leave a blank space, we're going to put a different term there. And technically we're answering the question, how many moles of water could be made if 5 moles of O2 react stoichiometrically with H2. So how many moles of water could be formed if 5 moles moles of O2 react stoichiometrically with hydrogen. We don't even have to say how much hydrogen we need. That's not really what we're interested in. Now we want to know how much water we can make. And of course, y'all answered this correctly. We can make 10 moles of water. Now, for products, instead of talking about the stoichiometrical amount, we give it a different name. We call it the theoretical yield. Please make sure you understand. The theoretical yield is also a stoichiometric amount, but it is the stoichiometric amount of product. And so that's another clue that chemists think we're giving to people when we ask you. We don't say, what is the stoichiometric amount of H2O that could be formed? We would say, what's the theoretical yield for this process? And then automatically we expect you to know, oh, theoretical yield, we're talking about a product, and that product theoretical yield is a stoichiometric amount that I can calculate based on my knowledge of an empirical set of molar coefficients. Everybody okay with all of this? All right. Now, the world would be a wonderful place if every time we actually do this type of calculation, we started with just the moles. And it's important that we start with moles for your understanding, because the molar coefficients are the molar ratio. And in chemistry, although we pay attention to the law of mass conservation, the moles, the amounts, are what really matters when we do these types of calculations. Right? Now in your textbook, on page 115, figure 3.8 on page 115. They have a schematic that we're going to pay attention to just the top 2/3. Right, so that's all on the front of the board. So we have reactant mass. We need to convert that to reactant moles. We leave this box out, but we can include it because we just basically did that. We calculated the amount of a second reactant. So we've done this bottom line already. We calculated or figured out the number of moles that could be required or that could be made of a product if we start with the amount of any other substance. So we basically have done this line right here. But as we've learned from lab, there's not some fancy device in lab that will measure the number of moles that we have to work with. It only measures the mass. It measures the grams. And so what we now need to be able to do is take the information we would collect in lab, the grams of reactants, the grams of products, and then tie it all together to this relationship between the molar stoichiometry. Now, there's no direct correlation between the mass of one to the mass of the other. We have to go through the moles. This is very important. Anytime that we are working with stoichiometry or stoichiometric calculations, either a stoichiometric amount or a theoretical yield, we have to get to the moles. Right? Now, we already know how to go back and forth between mass and moles. In each situation, we just need the molar mass for that particular substance. And in order to go back and forth between the reactants and the products, we need the molar coefficients. And so here's the deal. If we have any one of these pieces of information, we can calculate all the others because they're all related to each other. So, let's try it. Starting with 73.73 grams of hydrogen this time, not water. Hydrogen, H2. What is the stoichiometric amount of O2? I'll put parenthetically under here the longer version. How many moles of O2 are required to react completely? .73 grams of H2. So hopefully you can see the usefulness of the economy of words if we just ask, what is the stoichiometric amount of O2? We could also ask, what is the theoretical yield of H2O, which is a shorter version of how many moles of H2O can be made if 73.73 grams of H2 reacts stoichiometrically. With O2. So these are the questions that we're going to try to answer. Now, in order to do this, we need a balanced chemical equation because we need the molar coefficient. We also need to have the molar masses of all of our reactants and products. So, we've already seen this equation. Let's just go ahead and rewrite it one more time real quick. 2H2 gas plus O2 gas yields 2H2O liquid. And so I still have that 2:1 to 2 stoichiometry. We'll use this in the calculations. In terms of molar masses, 2 times 1.008 is 2.016. Oxygen, 16 on the periodic table, times 2, 32.00. And then water, we've already used this today, 18.02. And of course, the units here are all grams per mole. And so starting off with 73.73 grams of H2, we want to calculate how many grams of O2 are required to react stoichiometrically. What's the stoichiometric amount? And we want to calculate the theoretical yield of water. So, how many grams of water could be made if all of this reaction occurs? To answer these questions, we need this grid work. Right? So, I'm going to have to erase it, but you've got it in your notes to refer back to if you need to. This is what we're following. So let's calculate the stoichiometric amount of O2 first. What we basically have to do is take our 73.73 grams of H2, convert that to moles of H2, calculate the number of moles of O2 that that's going to make, and then convert that to the number of grams of O2. So there are 3 arrows in our path. That means we have 3 vertical lines in our dimensional analysis grid work. 73.73 grams of H2 goes in the upper left-hand corner. And then for the first conversion, I need the molar mass, 2.016 grams per mole. So my first conversion factor is my molar mass. Then I need my molar coefficients. Right? And what I find from my balanced chemical equation is that I need 2 moles of H2 for every 1 mole of O2. And then finally, I need to go ahead and convert from moles of O2 to grams of O2. So I need the molar mass. 1 mole of O2, 32.00 grams. Does everybody see the logic of how neatly this all fits together? And so all the principles that we've been using are now coming together. Grams of H2 cancel out with grams of H2, moles of H2 cancel out with moles of H2, moles of O2 cancel out with moles of O2, and we're left with our final answer, grams of O2. All right, so let's try to squeeze this in before I let y'all go for the day. We have 73.73 divided by 2.016. All right, I'm going to write that number here, which I'll compare 36.57, 242, 063. So that's how many moles of H2 correspond to 73.73 grams. Then I'm going to divide this number in half. That gives me 18.2862, 1032 moles of O2. 2-to-1 ratio, just like we need. And then finally, I multiply this times 32. And so the amount of oxygen required to react completely was 73.73 grams of H2. The stoichiometric amount of O2 required for this reaction is 585.2. Very good. All right. You know, we actually have more time than that clock is showing. So, from our balanced chemical equation, 2 moles of H2, 2 moles of H2O. That's a 1-to-1 relationship. So I'm going to go ahead and round this off just for convenience right now. 36.57 moles of H2 are going to be able to make the exact same amount of water. Not grams, moles. And then if I need to convert that theoretical yield from moles to grams, molar mass of water. So my theoretical yield of water is 659.6 0.035 grams of H2O. Everybody else coming up with a number that's pretty close to that? Anybody? I don't see any head shaking yes yet. Okay, now I do. All right. So, what I'd like for us to recognize here is the law of mass conservation. It says the mass of the reactants has to be equal to the mass of the products. So if I do 73.73 plus 585.2, I get 658.93. Here I get 659. Not exact. Round off there. We'll talk more about this next time. Pretty doggone close. All right. If anybody came in late, I still have some scantrons up here. Please return your calculators on the way out.